Imagine a box with 2 inputs and 1 output. You feed in 2 numbers, 5 and 3. You tell it add, out comes 8. You change the command to subtract, out comes 2. That's an ALU, an Arithmetic Logic Unit. Right now, it's sitting in your CPU, running billions of these operations per second. And right next to it is the control unit. The control unit doesn't compute anything itself, it directs. It tells the ALU what to calculate, tells other parts where to store values, where to move data. The ALU can compute, the control unit can direct, but right now, neither of them is doing anything. Something has to kick it off. That something is a process called fetch, decode, execute. That process takes less than 1 nanosecond. Let's slow it down and watch exactly one. It starts with a single number, stored in a single slot inside the CPU. That slot is a register, the fastest storage your computer has. And this specific register has one job: hold the address of the next instruction. It's called the program counter, or short, PC. It currently holds 100. That's in the RAM, where your entire program is sitting right now, every instruction laid out at numbered addresses. That means the next instruction lives at memory address 100. The CPU doesn't see the whole program. It just needs to know where to look next. To retrieve it, the CPU first copies that address into another register, the memory address register. Think of this as the outgoing slot. Whatever address is placed here is about to be sent to memory. At the same time, the program counter increments by 4 automatically. We'll find out why later in the video. The address 100 now travels out of the CPU onto the address bus, a physical set of wires that carries memory addresses from the CPU to memory. At the same time, the control unit sends a read signal along a separate set of wires called the control bus. What that means is, the CPU tells RAM, we want to retrieve something from you, in our case, the data from the address 100. Together, these tell memory, look up address 100 and send back whatever's stored there. Memory receives both signals, looks up address 100 and finds the instruction sitting there. 32 bits, just a sequence of ones and zeros. Memory places that instruction onto the data bus, a third set of wires. Unlike the address bus, the data bus goes both directions. It carries data from memory to CPU when reading, like in our case, and from CPU to memory when writing. The instruction arrives at the memory data register. The CPU's incoming slot for anything from memory, like a mailbox at the front door, everything from the outside lands here first. From there, it moves into the instruction register, the slot that holds the current instruction for the whole phase. Now the instruction is on the chip. But it's just bits, a raw sequence of ones and zeros. The arrangement of these bits isn't random. It follows a specific pattern. Which pattern depends on the processor architecture? There are 2 big ones: ARM and x86. ARM is what you find in pretty much every smartphone, every tablet, every smartwatch, and these days, in modern Macs too. x86 is what Intel and AMD build. That's what's running in your desktop, your laptop, in servers, in gaming PCs. The exact way bits are arranged inside an instruction is different between them. ARM packs them into fixed slots, always the same size. Every field has its place. For example, the bits in the second box tell the CPU what operation to perform, like add. x86 is more complex. The bits get split up too, but the way they're split can be totally different each time. Some boxes always get bits, others only sometimes. We're not going deeper than that. It's its own rabbit hole. The point is, every architecture has its own way of organizing the bits. But the job is always the same. The control unit has to pull out 2 things: what operation to perform and which registers to use. For our instruction, the answer is operation add and add the values in R2 and R3 and put the result in R1. You have probably no idea what R2, R3, and R1 means, so let's look at the registers we already know: the program counter, the memory address register, the memory data register, and the instruction register. Each one of these has a fixed job. But the CPU also has general-purpose registers. These are the flexible ones. What that means is, they hold whatever values the program is currently working with, like a result of an instruction. They're labeled R0, R1, R2, and so on. The difference between these 2 types is that general-purpose registers can hold whatever value for whatever reason. So back to our instruction. Now it makes sense. The operation is add. So we take whatever values are sitting in R2 and R3, add them together, and put the result in R1. Other instructions work differently. A load instruction, for example, actually grabs a value from memory and puts it into a register. So if memory address 104 holds the number 42, a load instruction can pull that 42 right into R3. That's how values get into registers in the first place. The instruction add just operates on what's already loaded. Inside the chip, every component is connected through a web of pathways. But these paths aren't always open, they're gated. There's a tiny switch sitting on every wire closed by default, blocking everything. The control unit's job is to open just the right ones for this specific instruction. So when the control unit says send R2 to the ALU, that's when the switch opens and current flows through the wire. For our instruction, the control unit opens the path from R2 to the ALU, the path from R3 to the ALU. It also tells the ALU add these two together, and it opens the path from the ALU's output back to R1. Everything else stays closed. The chip is now wired up, ready for the values to flow and the result to land in R1. So now the ALU adds 5 and 3 together and puts the result 8 into R1. The control unit's job was only to open the path and tell the ALU what to do. But something else important happens at the same time. The ALU also sets flags based on the output. Flags are tiny 1-bit signals. They're yes or no answers about the result that just came out. 3 of the most common: 0, negative, and overflow. Look at the result of our instruction. Was the result 0? No, so the 0 flag stays at 0. Was it negative? No, 8 is positive. Negative flag stays at 0 too. Did it overflow? No, it did not. Let me explain. Imagine a register that can only hold numbers up to 15. If our result had been 17, it wouldn't fit. That's overflow. But 8 fits easily, so the overflow flag stays at 0 as well. The ALU is basically saying, clean result, nothing weird happened. There are more flags out there depending on the architecture, but these 3 give you the idea. So now, after the instruction is finished, a separate path of wires runs from the ALU to its own register, the flag register. That's where these flags get stored. They're there so the next instruction can react to what just happened, like if the last result was 0, do this, otherwise do that. In our case, no flag was triggered, they all stayed at 0. So we just saw the ALU add 5 and 3, but add is just one of many things it can do. The ALU also handles arithmetic, addition, subtraction, multiplication, division. But it also does something different, operations that work directly on the individual bits of a value. These are called logic operations. These are just a few of them. Let's take AND as an example. Give it 2 binary numbers, 1011 and 1100. The operation AND compares them bit by bit. First position, 1 and 1, both are 1, result is 1. Second position, 0 and 1, 1 is 0, result is 0. Third, 1 and 0, result is 0. Fourth, 1 and 0, result is 0. Final answer, 1000. The rule is simple. Both bits have to be 1 for the output to be 1. If either one is 0, the result is 0. AND is what's called a logic operation, the kind of operation programs use for comparing values, checking individual bits, or making yes-no decisions. Remember the program counter? It got incremented by 4 right at the beginning the moment its address was copied to the MAR. Here's what the instruction actually looks like in memory. It's just a long string of 1s and 0s. Each digit is a bit. It's the smallest piece of information a computer can store, on or off, 1 or 0. Group 8 bits together and you get a byte. Our instruction is 32 bits long, that's 4 bytes. And each byte takes up its own address in memory, 100, 101, 102, 103. That's why when the PC is done, it can't just move one address forward. One address would only get it to the next byte. That would be still inside the current instruction. To reach the next instruction, the PC has to jump 4 bytes ahead straight to address 104. But here's the thing, while fetch is happening, the ALU does nothing. While decode is happening, the buses are quiet. While execute is happening, fetch sits idle. While one stage is doing its job, the other 2 are just waiting. Most of the chip is always dark. That's enormous wasted potential, and it's exactly what the next video is going to fix. Subscribe.